Welcome friends, this is Atharva. Today we are going to learn about the simulation of a shell and tube heat exchanger in DWSIM. Before moving ahead, I would like to request you all to like, share and subscribe to the channel. This encourages me to make more and more such useful videos which will help people out there to get jobs. So moving ahead, what we are going to learn in this. So definitely we are going to simulate a shell and tube heat exchanger in DWSIM. Calculate outlet stream temperatures LMTD, overall heat transfer coefficient, heat transfer area and thermal efficiency. But before we get onto our actual simulation on DWSIM, I wanted you all to actually have a look at the structure of the shell and tube heat exchanger. In last video, we also saw a heat exchanger, but that was a simple counter current heat exchanger. But here the geometry of the shell and tube heat exchanger is a bit complicated, and before we proceed to our actual simulation, I think you should first have a look at it so that you will be able to appreciate different aspects when we will get on to the real simulation. So these are the stream properties which we will be looking at. These are same what we did last time. Water will be our cold source stream and methanol will be hot. These are the heat exchange properties, and these are some more properties which we will be looking at when we are talking about shell and tube heat exchanger. For example, number of tubes, then tube spacing, tube layout, square. Then you can see there are some confusing parameters like baffle spacing, baffle cut percentage. So these we are going to see how exactly this look like when we talk about a real heat exchanger. Okay, so we are on the screen where we are seeing the side view of a fixed tube sheet heat exchanger. So, so this is called as fixed tube sheet because you can see these tubes are actually grooved inside the wall, and that's the reason it's called as fixed tube. There are different other types of heat exchangers as well, but in order to keep it a bit simple and we are all able to appreciate a simple design, I thought I should stick to a simple design, that is a fixed tube heat exchanger. Now what happens, this is the shell side flow we call. So shell side liquid will be entering through this. So here methanol will be our liquid which we will make it enter through the shell side. The reason is because it is on the shell side and it is not entering through the pipes. Now how this liquid moves exactly? So when the liquid comes down here, it takes this path in this way. So you can see there are, and comes down from here. You can see there are some dotted lines. These are nothing but the baffle plates. So baffle plates are arranged in such a way that there is a resistance to the flow of the fluid so that the turbulence increases, and because of turbulence a better heat transfer efficiency is obtained. Now other thing is we have a tube side liquid. So let me just change the color first. So this is a tube side liquid. It comes from here, and you can see there is a wall in between. If you remove this wall, the fluid will get directly down from here, and that's the reason the wall is given. And there is another reason for this wall, I will tell you later, but for this purpose, so the liquid, our cold liquid which is water, will come here. It will enter from these tubes. You can see these tubes, and the water will then come out from this side, from each tube, and then it enters here, and then again it flows in this direction. That is, it will be a counter current flow, and here it is in this direction, and then it comes out from here, and then it comes down. So that's the reason it is a two pass. Two tube passes are there, so two passes tube, exchanger, and single plus shell side. So shell side, the liquid is passing only for once. That's the reason we call it as a single cell pass and double tube pass. Now there are some other things to be noted here. As I said that this wall is given here. If the wall is not given, then this part is closed, and the fluid will just fill up this area, and it will just pass for one time, and the fluid will exit from this side. There will be an exit which will be given on this side, of the flow. So this will be a single pass tube. So it will be having a single pass only. But in this case, the diagram which we are looking at is a double pass tube side heat exchanger and single pass shell side heat exchanger. Now another interesting factor is here, there are different ways in which these baffle plates that can be arranged. So let me go to our next slide. Now these are baffle types. So these are, you can see, this is the side view, but if you see the front view, it will look like this. There are holes drilled through which the tube actually passes, and the alternately this tube is arranged in this direction. We will also be looking at a 3D view so that the idea becomes more clear. And here are some different arrangements like double segmental baffle, then triple segmental baffle. Another type is disc and donut. So this is nothing but the disc in between. This is the disc, and these are the donuts which are given here on wall sides. And this is also one of the arrangement. So this is a basic design I wanted to share with you how it looks like on the paper, and now also we'll be looking at how it looks in a 3D space. So let me go to the window. So this is how it looks in the 3D. This is the tube bundle. Set of tubes is called a tube bundle, and there are different types of the arrangement of the tube bundle which can be seen. And then if I rotate this, now you can see this is how it is arranged. The square type arrangement we call it, which we have also seen in our problem in the the specifications where we have called it as a square type. And now you can appreciate how the baffles actually look like. It might not be clear from a side view, but now in 3D view it is clear. So these are nothing but the baffles, and these baffles are arranged in such a fashion. And okay, so this is how it looks like. These are the baffle plates, and as I said, the pipes are actually grooved inside this wall. So how does it help is, when you have a hairpin heat exchanger, the area required is very large, and another important aspect is the leakages. So here you can see the leakage points are pretty well covered because these pipes are grooved inside the wall, and they are packed in such a way that they don't leak. In hairpin kind of heat exchangers, there are a lot of leakage points. Okay, so with that, okay, so this is the full snapshot of how it looks like, and you can see the inlets here. That's how the fluid gets in. So this is a shell side inlet, and this is a tube side inlet. And okay, let us go back to our slide and see the parameters once again. So now we will be able to appreciate exactly what they say. So now you can see that, mm, that's what we saw, different baffle spacing. So baffle cut is nothing but, so if this baffle was full, it will be 100%. So this this much portion is removed from this baffle. So this is nothing but the baffle cut. So baffle cut percentage what we are taking is 25%. So 25% of baffle is cut. That's what it means. Now let us go to our simulation window in DWSIM and actually let us solve the problem. Now I am on the interface of DWSIM. I will click File, then New Steady State Simulation. Next, search for water. It will show up. So water. Let me click. Let me just select it, and now I will have to select methanol as well. Here is the methanol. Next. So we are using Raoult's law package. So double click on the Raoult's law. Make sure you double click, otherwise it will not get selected. Press next. System of units is C5. Press finish. Now I will have to add two material streams given on downside. This icon is here which helps us to specify a material stream. Just drag and drop two material streams. So one is our water stream and another is our methanol stream. So water in, I am renaming it. Flash spec is temperature and pressure. Temperature we said it is at 10 degrees Celsius and 1 bar. So I am just changing those values here. Mass flow is 15,000 kg per hour. Go to compound. The mole fraction, so the basis is a mole fraction and mole fraction of water in the water stream is 1 and methanol in methanol stream is 0. Click on accept changes. Then similarly click on the second stream. This will be our methanol in. Change flash spec temperature and pressure. So temperature is 80 degree and pressure is 5 bar and mass flow was 25,000 kg per hour. Going to compound amounts. In methanol stream we have mole fraction of methanol as 1, water as 0. Accept changes. Then I will also need the outlet streams. So I will just drag and drop. So this is my methanol out. And this is my water out. So I'm just changing the nomenclatures here. Now go to the downside. You can see the exchanger tab here. There is a heat exchanger tab. Just drag and drop. HE004. So I will just write HE. Then inlet stream 1 is methanol in. Inlet stream 2 is methanol out. Sorry, outlet stream 1 is methanol out. Then inlet stream 2 is water in and outlet stream 2 is water out. Now it's time to configure our heat exchanger, which is a shell and tube heat exchanger. So in calculation type, just click on that tab and select shell and tube exchanger rating and flow is counter current. Now go to, on downside we have edit shell and tube heat exchanger properties. I am clicking on that. Then there is shells in series, that is 1. Then shell passes. shell passes, that is 2. So I am considering a 2 shell pass. And then internal diameter of shell. So internal diameter of shell, as we said, was 1000 mm. Press enter. Fouling factor is 0.00 and 35 Kelvin meter square per watt. And baffle spacing, we said, is 250 mm, which is selected. Then baffle cut percent is 25. Then tube internal diameter. Then tube internal diameter. Let me take this as so we have external diameter here. So external diameter of tube is 20 mm we are considering. And the tube thickness is 2.5 mm. Then length is 5 meter. Then fouling factor is again 0.00035. Roughness is 0.05. Thermal conductivity is 60. Then passes per shell, we said 2, and tubes per shell will be 1024. There is any shell passes, we are considering 2, and tube spacing is 25 mm. Roughness we have taken. So tube layout is square. So fluid in tubes is cold. Okay, that I will not change. And tubes internal diameter. So this should be 17.5 because tube thickness is 2.5. So external diameter of tube is 20 mm. So internal diameter with that logic should be 15 mm. So we are ready with our configuration now, and we can simulate this. So let's see what results we get. So thermal efficiency is 77.997 and log mean. Now let us go to insert and insert a property table. I am just double clicking on that. HE. Then I will select heat exchanger. Let me see global transfer heat load, cold fluid, hot fluid, and I think that should be enough. The thermal efficiency. Okay, let us see what are the results. Okay, so hot fluid outlet temperature we got is 41.53, and the cold fluid outlet temperature 65.4403. We can also insert more master property tables. water in, methanol in, water out. I am selecting everything: temperature, pressure, mass flow, molar flow. Molar fraction mixture, water. Then molar fraction mixture, methanol. Okay, so this is our another property table. So this is how you can see different properties of. Now what we can do is, let me just show you why it is important that we should select a proper baffle spacing and baffle sizes. You can see the hot fluid pressure drop is 0.03023 bar and cold fluid pressure drop is 0.0005 bar. So now if I increase the baffle spacing, for example, if you ask me this question, that why not increase the baffle number of baffles, and we can actually get a better heat transfer area, or heat transfer efficiency will improve because the more turbulence will be generated. Now let me just reduce the baffle spacing. So if I say 100 this means that more baffles will be able to fit now, and you can see the hot fluid pressure drop has increased now. Just a minute. Baffle spacing is 100. Press enter. Now I will. So hot fluid pressure, and let me just resolve it. Now you can see the hot fluid pressure is actually increased. It is now 0.190422. Now let me add more baffles. So here, to add more baffles, I am just reducing the number of baffle spacing so that the system gets the information that more baffles needs to be added. Press enter, close, and then just click on solve flow sheet. Now you can see it, the hot fluid pressure drop has increased 0.9 to 0. It's near to point, it's near to 1 bar now, and when it was 250 this means less baffles were there, it was around, I think, 0.002. So it's some few tens of folds increase in the pressure. So the pressure increase is actually having a greater impact on the cost side. So if you change different parameters here, you will find the pressure drop will keep on increasing or decreasing, and it varies in certain fashion. So so that's all for this tutorial. I hope you liked it, and please kindly like, share and subscribe to my channel. Thank you very much. Let's meet again.